Myself, Narayanan, Assistant Professor, Department of Mathematics, Bishopur College, Trichy. Yeah, in this lecture, we are going to see linear algebra, especially the content of vector space, subspaces, dimension, like this toy. Okay. Before we are starting with the vector space, first we can see the difference between the vector space from group. How is this different from the groups, rings? Okay. What is the meaning of group? Group means we are going to study one set with one binary operation. That is a group. Ring means it is a study with one set with a two binary operation. But the vector space is a difference from these two definitions. Vector space is going to study with two sets with a two binary operation. One binary operation is called vector addition. Another binary operation is called scalar multiplication. So vector space is different from group and rings. Okay, now we can see the definition of vector space. Vector space. A vector space is, or another way of calling the vector space, is a linear space consisting of the following: a field of scalars, a set V of objects called vectors. Third one, an operation called vector addition in such a way that addition is commutative. That means the commutative property I have listed here. And addition is associative. The associative property of addition is listed here. There exists a unique vector, 0 belongs to V, that is the identity element of the vector. 0 belongs to V, called the 0 vector, or another way of called additive identity, such that alpha plus 0. This is the definition of the identity. Then for each vector alpha belongs to V, there exists a unique vector minus alpha belongs to V, such that alpha plus minus alpha equal to 0. That minus alpha is called inverse, additive inverse of the V. An operation called scalar multiplication in such a way that 1 times alpha equal to alpha. Here there is a scalar multiplication operation is defined. C1 C2 times alpha, that is a C1 of C2 of alpha. Also another two distributive laws. These are called distributive laws. Okay. So if we satisfy all these three all the conditions, then V is said to be a vector space. Okay. Here we have to notice that the important way is vector space over some field. Okay. So we can see the examples. First one, let F be any field. Okay. An n-tuple scalar Fn is a vector space over F. The element in this vector space should be n tuples. For example, you can replace here, instead of F, you can put R, set of all real numbers. R power n is a vector space over R. Okay, the second example. It is a very crucial example. The space of m cross n matrices. It is denoted by F power m cross n. That means set of all m cross n matrices which entries or varies from field F. Here also you can replace instead of F, R. The set of all n cross n matrices over R is also a vector space over R. The next examples. Okay, the next definitions. A vector beta belongs to V is said to be a linear combination of the vectors alpha 1, alpha 2 up to alpha n. Each alphas are vectors in V. If there exists a scalar C1, C2, Cn, these are all scalars from field, such that beta can be written by alpha 1 V1, sorry, C1 V1. Next we can see the definition of linear combination. A vector beta belongs to V is said to be a linear combination of the vectors alpha 1, alpha 2 up to alpha n in V if there exists scalar C1, C2, Cn in F. These are scalars are in F, such that beta can be written by C1 alpha 1 plus C2 alpha 2 up to Cn alpha n. That means any vectors beta in V can be written by like this way. This can also used by written using by the notation, summation notation way. Okay. Then the next definition, subspaces. Let V be a vector space over the field F. A subspace of V is a subset W of V, which itself is a vector space over F. That means a subset W of V is said to be a subspace of V. W itself is a vector space. That's all. Within the operation of the vector space, the whatever the operation we are used in the vector space, it is same as the W. That's all. Okay. Then the next important one theorem, this is a very important crucial result in the condition of checking of the subspaces. What is the condition is, a non-empty subset W of V is subspace of V if and only if for each pair of vectors alpha comma beta belongs to W and each scalar C belongs to the field, the vector C alpha plus beta belongs to W. This means that if it is enough to check only this one condition, it is enough to check all other conditions of the vector space. That means if enough to check this condition, it is a subspace of V. Okay, we can see some other examples of the subspaces of the vector space. If V is any vector space of V, then V itself is a subspace of V. This is a non-trivial subspace. It is also called the non-trivial subspace. The given vector space can be also considered as a subspace of V. Second one, the subset consisting of the zero vector alone is also a subspace of V. It is called zero subspace of V. This is also another non-trivial subspace. The first example and second example are called non-trivial subspaces of the vector space. Third one, an n cross n matrix A over F is symmetric. This means that the collection of symmetric matrices, for all the collection of symmetric matrices form a subspace of the collection of n cross n matrices. Here I am considering the vector space as a set of all n cross n matrices. I am only collecting the symmetric matrices as a subspace of the vector space. Okay, then next, similarly, and the next example, I am going to collect as a set of all n cross n matrices over the field of C of complex number. Here the n cross n matrix is a Hermitian. Hermitian means A equal to minus A transpose. Yeah, A equal to A transpose for all. The next example is the collection of n cross n matrices over the field of complex numbers. I am collecting only the Hermitian matrix, or it is a self-adjoint matrix. What is the meaning of Hermitian matrix is the transpose Aij equal to Aj bar. Okay, this is called the Hermitian matrix. I am collecting only the Hermitian matrix. This is also a subspace of the vector space. Here the vector space is set of all n cross n matrices. That's all. The set of all n cross n complex Hermitian matrices is a vector space over the field of, or is also real vector space. Okay, next we can see the definition of spanned vector. Let S be the set of all vectors in a vector space V. The subspace spanned by S. That means S spanning S, the set S spanning the subspace. Okay, spanned by S is defined to be the intersection W of all subspaces of V which contain S. When S is finite set of vectors, that is S equal to alpha 1 alpha 2 alpha n, we shall simply call W subspace spanned by these vectors. Okay, the next definition, basis and dimension. This is also one of the important topic in the vector space. Okay, we can see the definition of basis. Before we are seeing the definition of basis, we have to know what is the meaning of linearly independent, linearly dependent, everything. Okay, so first we are going to see the definition of linearly independent. Let V be a vector space. Here I am shortly using the notation Vs. That means it is a vector space. Let V be a vector space over F. A subset S of V is said to be linearly independent if there exist distinct vectors alpha 1 alpha 2 up to alpha n belongs to S and scalar C1 C2 up to Cn belongs to the field, not all 0, such that C1 alpha 1 plus C2 alpha 2 up to Cn alpha n equal to 0. This is called the linear combination. Linear combination equal to 0, which means a set which is not linearly dependent is called linearly. Next we are going to see the important definition of the vector space, basis and dimension. Let V be a vector space over F. A subset S of V is said to be linearly independent if there exist distinct vectors alpha 1 alpha 2 up to alpha n belongs to S and scalar C1 C2 up to Cn belongs to F, not all 0 scalars, such that the linear combination is 0. That is C1 alpha 1 plus C2 alpha 2 up to Cn alpha n equal to 0. If this condition satisfied, these alphas alpha 1 alpha 2 up to alpha n are said to be linearly independent. Okay, whenever this condition is not satisfied, these are called linearly dependent. A set which is not linearly independent is called linearly dependent. here we have to importantly note that the linearly dependent means there exists some non-zero scalar. Linearly independent means all the scalars should be 0. Linearly dependent means there exists some non-zero scalars. Okay. Then next we can see S is linearly dependent if and only if C1 alpha 1 plus C2 alpha 2 up to Cn alpha n equal to 0. That means C1 C2 up to Cn equal to 0. Okay. Next we are going to see some notes. Any subset of a linearly independent is linearly independent. If we are considering a set S is linearly independent, also we can take some subset of S, that yet the subsets should also be linearly independent. Any set which contains a linearly dependent set is linearly dependent. Here S is a linearly dependent set, W is a superset of S. That means W is also linearly dependent. Next, any set which contains the 0 vector is linearly dependent. It is a very important result. A set which contains 0 is also a linearly dependent. A set S of vectors is linearly independent if and only if each finite subset of S is linearly independent. Okay, the next definition. It is now I am coming the important part of the linear algebra, the definition of basis. Okay, let V be a vector space over F. A basis for V is a linearly independent set of vectors in V which spans the space V. The space V is finite dimensional if it has a finite basis elements. So basis means it has to follow the two conditions. The condition number 1 is it should be linearly independent. The another condition is it should be span the vector space. If these two conditions are satisfied, the set is called basis. The number of elements in basis is called dimension of the basis. That means if the number of elements is finite, it is a finite dimensional vector space. If the number of elements is infinite, it is called infinite dimensional vector space. The number of elements is called dimension of the vector space. Okay, we can see some examples. In this example, I am considering the F3. The vectors, first vector alpha 1, it is a 3, 0, minus 3. The second vector alpha 2, minus 1, 1, 2. And third vector alpha 3 is a 4, 2, minus 2. Alpha 4 is another vector 2, 1, 1, or linearly dependent vectors. Since I am considering one or the linear combination is 0. I am calculating this linear combination value. This value is 0. But in this linear combination, there exists some non-zero scalars. You can see the first scalar 2 is non-zero. Here also the 2 is non-zero. Here also the minus 1 is non-zero. But here I am taking 0. Okay. It at least there exists one scalar non-zero means it is a linearly dependent. Here I am getting more than one scalar non-zero. So these 4 vectors are linearly dependent. The vector, I am considering another example. The vector, it is a E1, that is a 1, 0, 0. The vector E2, that is 1, 0, 1, 0. The vector E3, 0, 0, 1 are linearly dependent. You can write the linear combination. Thank you.